Hi, everyone. We're going to begin our fourth session of the AIA 2030 commitment web series here in a minute. We have Martin Torres with Austin Energy to give us a presentation on embodied carbon and how that kind of ties into the 2030 commitment and some other structural engineering side of that and some strategies. And then we'll break out into breakout rooms and have kind of a meet and greet type thing and have able to ask questions and kind of go over that a little bit more after Martin gives his presentation. So I need to thank our committee sponsors, Indoor Weather Professionals, Pilgrim Building Company, and Hill and Wilkinson General Contractors. So thanks for being our sponsors for COTE, and we'll get started. I'll turn it over to you, Martin.
Awesome, thanks, Josh. Here, can you stop sharing so I can share? Okay. Here we go. Is that coming through?
Yes.
Okay.
Yes, it is.
Cool. So yeah, I'm going to talk today about embodied carbon, biogenic carbon. So how does timber fit into this whole thing? Some reduction strategies and also policy. Where does policy stand and what are we doing here in Austin? To give a little background on myself. So I'm Austin native. I'm one of the unicorns. My background is in structural engineering. So that's what I studied. I went to Rice for undergrad and then Berkeley for my master's, and then worked as a structural engineer at Walter P. Moore. But in tandem with that, I was also doing a lot of LCA work and sustainability consulting. And I sort of fell in love with reducing embodied carbon. My mom is a tree hugging hippie and some of that rubbed off. So sustainability is really important to me. And I saw an exciting opportunity. So now in my role at Austin Energy, I am purely focused on embodied carbon reduction policies and initiatives and different things like that. In the fall, I'll be starting my PhD at CU Boulder, and that'll be with Will Schrubar, and I'll be studying LCA data methodology. How do we deal with these numbers? But more specifically, how do we deal with uncertainty and error propagation? So the agenda, I'm just gonna go quickly over some embodied carbon basics. What is it and why is it important? Then we'll dig into biogenic carbon, how timber fits into the situation, go over some reduction strategies for different materials, and then some policy efforts, specifically what the Carbon Leadership Forum is doing globally and also here in Austin. So I'm sure a lot of people here have seen this graphic, but just very quickly, embodied carbon is the upfront carbon that's associated with building materials as opposed to operational carbon that you see over the whole building lifespan, which could be 60 years, but it's all the energy use rather than the materials up front. And the important difference between these two things is the upfront emissions is all right before the door, or it all happens before the door opens. And then the operational emissions happen over the building's lifespan. And the timing is really important. When we think about all the goals that we're setting by 2030, by 2050, when we need to hit those marks, then especially for new construction, that big bar at the front is a lot more important. And so specifically for new construction, between 2020 and 2030, embodied carbon is 74%. By 2050, it's about half, 49%. So for new construction, embodied carbon is a huge piece of the puzzle. And I'm not saying operational carbon isn't important. Improving those efficiencies is really vital. Refurbishing is really important, but this embodied carbon needs our attention too. So I talk kind of ubiquitously about embodied carbon, but it's not just the carbon. Global warming potential, CO2 emissions is really important. That's what's driving climate change, but there are other environmental impacts as well. So when I say embodied carbon, that is what I'm talking about, but there are all these other impacts that are happening as well. So non-renewable energy demand, eutrophication potential, acidification potential, smog formation. Ozone depletion is sort of getting phased out. Buildings aren't shown to have a huge contribution to that, but it's still something that's tracked traditionally in LCAs and EPDs and whatnot. So all components of a building are not created equal when it comes to embodied carbon. If I'm eating 40 cheeseburgers a week, the first step in my diet plan should not be to measure the oil and vinegar that I'm putting on my side salad. It should be cut out the cheeseburgers, right? So when it comes to embodied carbon reduction, like let's focus on the big picture first. So much of it is coming from the structure, So a lot of these, a lot of the reduction strategies are focused on structural material, and that's the reason. We want to proportion our efforts to the outcome. And when we think about sort of the global importance of why embodied carbon, we're building a whole lot. And I mean, one of the best strategies to reduce embodied carbon is just using an existing building. The reason for that being you've already like spent that carbon, it's already up in the atmosphere, so might as well take advantage of it. But we're building a whole lot. And in the US, we might be able to reuse buildings, but with a lot of urbanization and especially in the global South, they're gonna have to build a lot. And what I wanna emphasize here is just this is a global problem and it's gonna require global solutions. And so a lot of our reduction strategies, like let's share our best practices, let's create a community around this. That's where, and I'll talk about this later, but something like the Carbon Leadership Forum steps in to share these best practices so we can sort of have this community of understanding how we can respond. It's not just one person that wins the race. It's got to be all of us crossing the finish line. And even here in Austin, I'm sure this comes as no surprise to anybody, but Austin and Central Texas is growing a whole lot. A lot of people are moving here, and that's going to take a lot of new construction. So this is a very pressing issue globally, but also locally. And when we look at global CO2 emissions, embodied carbon is a really big chunk. So we see the building operations, that's the 28%. That's where I say, I'm not saying embodied carbon is the only important thing, but it's still 11%, and that's huge. And if we look at some of the common materials that are being addressed with embodied carbon, like concrete, steel, and aluminum, that ends up being 22%. So even outside the building industry, the way these materials are getting used is really widely impactful. So if we can make changes to update these supply chains and improve the process and improve tracking information, it's going to have implications beyond just the building industry, which I think is really important to understand. But there are 1.5 million issues that we could be dealing with. There are so many things happening in the building industry. So why embodied carbon? And so I want to offer sort of a thought framework that I've used to bring to this conversation that I find really valuable. And that's that the most pressing problems are big, neglected, and solvable. It needs to be big because otherwise that means there's more to be gained by solving the problem. It's important that it's neglected because with more people addressing a problem, you start to get diminishing returns, and embodied carbon is certainly a neglected problem. And it needs to be solvable, because if it's not solvable, then what the hell are we doing? We're wasting our time. An example of something that wouldn't be solvable is something like aging. Aging presents a lot of health concerns, but it's a really difficult problem to solve. So whether or not we should put resources to that, but that's a whole other conversation. So there's an overview of embodied carbon, why it's important. So now I'm going to dig a little bit into biogenic carbon. So biogenic carbon it's carbon derived from or contained in biomass being material of biological origin. So generally what this refers to is wood, timber, mass timbered, CLT. And it's important that we talk about wood because it's made up a lot of residential construction for a long time, but there's also an increasing popularity of mass timber products like CLT. And it's a really appealing material for carbon reduction, but it's not a silver bullet. And that's part of what I want to dig into. It's really important to understand all these complexities of wood, what our current knowledge gaps are, what steps we can do right now, and then what we need to keep in mind as we move forward. So if you look at CLT production in the US, or CLT buildings in the US, you can see that they're starting to pop up, but not quite everywhere. It's gaining popularity. People are sort of tiptoeing, but in the top right here, you can see there are 2 new CLT plants happening, but it is growing, and there are people using these ideas, and there are design guides out there and ways to promote CLT. So it's growing, it's happening, it's gaining popularity. But to take it back of how is this biogenic carbon even working? So in a forest, we're all familiar with the process of a tree is basically breathing for us. It takes in the CO2. But what I want to highlight here is that oftentimes a forest sort of stores, you can't think about it as just a collection of individual trees. You need to treat the forest as a mass in and of itself, because the forest's ability to store carbon is greater than just a single tree. And the reason for that is a lot of the storing capacity happens in the soil, below ground, in the roots. And that's because it's really ecologically diverse. There's a lot going on. And so when it comes to sustainable forestry practices, this is one of the big reasons it's so important, is if you're not facilitating this ecologically diverse forest, then it reduces its ability to store the carbon. So if we're just wiping out a whole bunch of trees without replenishing it and understanding the importance of that ecosystem, it can actually be really damaging. And so if you look at carbon over the life of a wood product, you can see on the left, this is looking at a primary forest or like an old growth forest that's been there for a lot of time versus afforestation or growing a new forest where there wasn't one before. And you can see the carbon storage from the beginning and then to the end. And I want to be clear, this is oversimplified, but what I want to emphasize here is old growth forest, there's a lot of carbon storage potential. And if we start, there's a bad way to get in there and get the timber products. And so it's not just as simple as I'm storing wood in my building and that's saving the world. If you're getting it from a bad source, then it can actually be harmful. And I think what that highlights is the importance of afforestation, building or growing new forests, and making sure they're done in a sustainable way. And when we see the carbon over the life of the wood product, so we plant it, it starts storing carbon, so it goes negative, but then it manufactures, it starts going up. Again, this is really oversimplified, but that's generally how this process works. Now, if we move that into the context of an LCA, then we think about in different modules. So there's module A, which is manufacturing and processing, B, which is maintenance and reuse, C, which is end of life, and D, which is outside of the building system. So looking at recycling and reuse. This is sort of what the biogenic carbon story looks like. So biogenic carbon enters the system as carbon stored in trees. So it's sucking in that carbon. Then it gets processed, it gets shipped. There are fossil fuel emissions there. It's burned, there's waste. And then throughout this process, you can see that it's emitting carbon the whole way. Hopefully by the end, it's storing that carbon, it's maintaining it. Hopefully we're not burning it at the end of life and putting it into the atmosphere anyway. But this is where that biogenic carbon moves throughout the process. Now to tell the story of, so we start here with 1.86 cubic meters of wood. We'll end up with 1 cubic meter of finished CLT. And the reason for that is that we're transporting it. We need to cut it into dimensional lumber. There's wood lumber that's cut as waste. And so you can see how there are some inefficiencies in here. And there are also all these emissions happening along the way. So this graph just shows your typical inputs. So we have our fertilizer fuel, diesel fuel, there's fuel, and there's different glues and different joints that are put in, because CLT is there, it's sort of stacked timber going in different ways that's glued together. But you can see how there are all these inputs and outputs throughout the system. It's not just as simple as we're storing carbon. There is waste, there's fuel use, and all sorts of things. So again, this is kind of a broad depiction of how biogenic carbon moves throughout the system, but there are different methods of actually accounting for it. So what happens when we have an LCA? How do we actually do it? So there are 4 different methods shown here. So the top left is called the zero approach, or the carbon neutral approach. And that basically assumes that the release of CO2 from a bio-based product at the end of life is balanced by the equivalent uptake at the beginning of life during the biomass growth. And so there's no consideration of biogenic uptake or release. And so it just doesn't do much to account for it. In the bottom left, it's the -1+1 approach. And so this takes into account the uptake of biogenic carbon in module A, and then reports the release of the biogenic carbon in module C. So at the end of the life, of the building, the biogenic carbon is released, and the carbon content is further transferred into the subsequent product system, in this case, or in the case of recycling. But one of the problems with this is if you're using this sort of system and then you're only considering module A, which is often, which can happen in either EPDs or LCAs, then you're giving yourself that benefit without understanding the whole picture of the carbon. And so you kind of cut it short and you're not painting the full picture of these assumptions. So those on the left, that's sort of how it's dealt with in traditional LCA softwares right now. On the right they're dynamic LCAs. And so they have, it thinks to understand them, you really need to think about what's actually happening with the CO2. Where does it start? How long is it stored? When does it get sucked up by the forest? And so it actually uses like time-dependent characterization factors that are basically used as multipliers for the biogenic carbon that you'd achieve in a more simple approach. And so this takes into account something like rotation period for the forest. So how long is it taking the forest to grow back? When is it going to be able to suck that CO2 back in? And then also the product storage lifespan. So how long is that building going to last? And so with these dynamic factors, it's able to give a more robust understanding of how is the biogenic carbon moving? What is the storage capacity? And what's our actual emission over time? The two scenarios that can be considered are, so there's one that assumes that the trees grow before the use of the harvested wood product. So that's when we're accounting for tree growth, following a natural carbon cycle, and that's in the top right. Or number two, which is accounting for regrowth after harvesting, assuming an equal amount of the harvested trees would start growing right after the production. And so did the trees grow before or after? It's just a way to simplify it. Obviously both are happening, but how are we accounting for it in our system? And so looking at how these different methods compare, this is from a paper published, I think, last year. And so just looking at the massive differences between the 0, -1 + 1 compared to the dynamic approach. And the dynamic approach is really where the industry is heading. That's considered by academics to be a lot more robust and a lot better accounting of what's actually happening with the CO2. But you can see these huge differences. And so when we're doing LCAs right now, and we're generally using these first two approaches, I think what this does is it just highlights how much of the picture we're missing. And the logic behind the huge differences is mainly due to that time parameter that's being used and the influence of wood residues from wood processing. Like, how are we dealing with all this waste? But needless to say, there are really big differences and not everybody necessarily agrees. Between the dynamic approaches, a good way to visualize that is here. So are we accounting for the uptake before construction or after construction? Here you can just see the line moves. Before here, it stays 0, and then it starts moving. So that's just the difference between those two approaches. Whether one's right or one's wrong, it's hard to say. They're just different assumptions. Now, when it comes to these dynamic approaches, they're not currently available in LCA tools like Athena or Tally, but there is an Excel tool, and I'll drop a link in the chat after at the end of the presentation. But the World Wildlife Organization has this Excel sheet where you can put in a lot of these different parameters, play around with it, and give a more robust understanding of what's happening with the wood. It's not perfect, but it's definitely a step in the right direction, and it's definitely where a lot of academics see this going. So let's take it back to the real world, because when we're doing LCAs, you're using Athena or Tally or maybe OneClick. But even within these softwares, a lot of different assumptions are being made. And the main thing I want to highlight is, because what it comes down to is how much carbon is being stored. How much are we keeping onto? Where can we get that negative value? And if you look at Athena, we're getting 70% of the original CLT is permanently stored in a landfill. So that means we're sucking up that 70% of the carbon. For Tally, it's like 32% of the original CLT. So it's a huge difference. And both of these are acceptable softwares. Both of these are fine. They're just making different assumptions for how much is going to a landfill, how much of it is anaerobic versus aerobic, what's happening with the decay. And not to say that either is right or wrong, but it's different, and it shows just how much variability there is in this whole process. And if you actually do an LCA, so there were a series of case studies done by the Tallwood Design Institute. So there's each of these chunks that represents an LCA, and so you can see modules A to C versus A to D. So are we accounting for that end of life, or the recycling and uptake at the end of the life? But you can see how big these differences get, and it's also included with and without biogenic carbon, because Tally allows you to do that. But there are huge differences. Like, they're not to say any of these is right or wrong, but there's nobody's really agreeing. And so I just want to highlight how important these assumptions are and understanding how much there is to know. So looking at, or elaborating, I guess, on some of the knowledge gaps. So this is presented as, well, what do we need to learn, and what do we need to do to deal with wood better, do a better job dealing with wood? So we need more transparency and transparency of impacts of pesticides and fertilizers. They're sometimes included, but not always. And this is partially addressed by certifications like FSC and SFI, but there are a lot of chemicals that are still allowed. And this is where it ties into some of the other environmental impacts that I mentioned earlier, like eutrophication, acidification. What are these fertilizers doing? And the recommendation here, and this is going to be kind of a consistent message, is we need more transparency. We need more data. This can come through certifications like FSC if we lean on those, but it's important to understand where they need to grow. And then linking complex carbon models to CLT and wood product use. So when I talk about where are all these assumptions coming from, the full context of the biogenic carbon storage is really difficult to fit into our design decision process. So current LCAs of CLT don't tell the whole story. And this can include biogeophysical factors like surface albedo, surface roughness, evapotranspiration, land use change, whether that's direct or indirect. And all of these are site specific, so it depends on where you're getting the wood. And so because it varies so much, it matters where it's coming from. And then also stored carbon content. We generally assume 50% of the wood tissue is stored carbon, but this is approximate. It can range between 46% to 55%. So there's a range there, and understanding like what values are specific to this tree species, creating a robust reference database to use for EPDs rather than just tossing the 50% out there because it sounds pretty. And then the timing of biogenic carbon and fossil fuel emissions. I mentioned this earlier with dynamic LCA, because we need to understand the forest rotation period. How long does it take a tree to grow to maturity? The product storage time, how long is it actually being stored in the building? Is it being reused, or is it getting tossed in the landfill? Then how much is decaying? So let's put dynamic LCA models to work. Like this is being developed. It's not commercially available, but it's there. So yeah, I'll link that tool in the chat. But that's another part that is important. CLT carbon storage in landfills. Is it decaying? How is it decaying? How much is decaying? It depends on the landfill. Depends on the wood. And so the decay of CLT needs to be further researched and modeled with excavated samples from active landfills. We just need a better understanding of those to make better assumptions and paint a better picture. Life cycle data for all stages. So I've mentioned this before, but looking at the whole picture, where is all of this information falling? So CLT manufacturers need to include all of the CLT's life cycle in their cradle to grave EPDs if possible, especially with multiple stage C scenarios. What are you doing at the end of life? Lack of LCAs, we need more LCAs. That's an easy one. Everybody should be doing LCAs. And then impacts of the sealants, finishes, and metal connections. This is something that's largely ignored. It's not a huge piece of the pie, but if we want to paint this more robust picture, it's still an important part. And then LCA and CLT data. We just, across the board, we need more data. We need to be more robust in our approach as we move forward with wood. But what can we do now? So select CLT from sustainably managed forest, make sure it's FSC certified. FSC isn't a perfect certification, but having a certification to lean on and pushing it to improve is kind of the best route to go. Design for reuse, design for recycling is really important. Design with specific sizes, avoid waste. There's a way to use interlocking CLT that doesn't require adhesives. I've never done this and I haven't personally seen it, but avoiding those glues and laminates is good. And if you show off your CLT, expose it, don't use gypsum. Choose regional manufacturer. There are more CLT manufacturers it's something that's growing. Air dry the lumber to avoid more fuels being used. And there are ways to upgrade the drying kilns and power, but I know that doesn't usually fall on the designer. Okay, that's timber. You're all timber experts now. But looking at embodied carbon reduction strategies more broadly, not just with timber. So the best thing you can do is just not build. We need to build less. So reuse buildings. But if you do have to build, then try to find an existing building that you can use, and reduce and replace, specify or design for deconstruction, use existing materials, use salvaged materials, reuse products. And then the last step is requiring low carbon products. So if I am going to get concrete, then make sure it's low carbon concrete. But that's the last thing that you can do. I think prioritizing this early action can be really valuable. And when we do this, how we track this information is through EPDs and LCAs. And basically what you're doing, you're just getting material quantities, you're multiplying that by an impact, and then you have your building impact. It's that simple. It's not quite that simple. But because where are you getting the data? Where is it coming from? But this is basically the process that we need to go through. But when we need more LCAs, we need more EPDs to make this more feasible. Because a lot of time the impact numbers that we're using are industry averages, or and it's a lot better if we can get more product specific and we can be more transparent about where it's coming from, because that can start to drive change of specific materials over time. So yeah, LCA overview, what are we doing? So you have your initial assessment. So what's the goal? What's the scope? How big is the building? What are we're including foundation, structure, enclosure. So define the building. How big is it? What is the end of life scenarios? Are we designing for deconstruction? Determine the environmental impacts. So kind of figure out what LCA tool, figure out what assumptions you're making. How are you incorporating biogenic carbon if you are? Interpret your results. So do it early on, understand where your impacts are, reduce accordingly, and then prepare your reports. So looking at specific materials, concrete, it's about cement. It's not fly ash replacement. It's about total cement. Fly ash is a great way to get to total cement, but it's about the total cement requirement or total cement content. And you can do this in a variety of ways: longer cure times, optimize base bands. I think that's a huge one. Optimizing material usage, so optimizing your base bands, making sure you're using as little material as you can. And then SEM replacement, using carbon or CO2 injection like carbon cure, performance-based requirements, so you're not getting strengths that are just way higher than you need them to be. And then also using Portland limestone cement. This is something that's available in Austin. There's a producer that has Portland limestone cement. Steel, you use steel from an electric arc furnace rather than a basic oxygen furnace, and that really comes down to the type that you specify. If you have HSSs, those are usually going to come from a basic oxygen furnace. So look at wide flange, look at recycled steel. Use braced frames instead of moment frames. That's usually, I think, something like 12% less material. Use joists and truss members instead of rolled shapes. Size members more precisely. Use higher grade steel. As steel gets stronger, the impact doesn't really go up. So if you use stronger steel, you can use less material. And then design for deconstruction. That's something I want to keep emphasizing, but making sure that your building has a life after, or at a second life at the end of its life is really good. Wood, talk about this a lot, but reclaimed wood, local manufacturer, make sure it's FSC certified. And some sort of secondary high impact materials. Insulation, stay away from high intensity HFC blowing agents. Use carbon sequestering insulation like wood, straw, clay, straw, hemp, cork, wool. Avoid like EPS, XPS, polyiso, structurally insulated panel systems with foam insulation and spray foam. So leaning on those more natural materials is usually good. Gypsum, lightweight gypsum, use thin gypsum, specify fewer grades, make it easier to recycle. For envelope, generally speaking, reduce aluminum and glass use. Those are, when it comes to the envelope, those are pretty high impact materials. And for carpets, there are low carbon carpet tiles. But like I said earlier, if you're don't get too into the weeds of measuring your oil and vinegar on your side salad before addressing your the 40 hamburgers you're eating, and that's really from the structure. So Carbon Leadership Forum policy efforts. So Carbon Leadership Forum is a organization that I've been involved with for, I guess, a couple of years now, and it's a global it's international. It's kind of an industry academic partnership just aimed at like, let's decarbonize the built environment. Let's talk about embodied carbon. And the way it does this is through it kind of has 4 pillars. So they do research. There's an academic side of it. They provide resources for designers. There's a network, and that happens locally. We have a chapter here in Austin, or a hub here in Austin. But then there's also an online community where you can, it's kind of called like the Google search of embodied carbon, where you can start conversations and make posts and interact with people all around the world. And then different initiatives. And so to talk about some of the initiatives, some of these are policy initiatives. So there's SE 2050. This is like Architecture 2030 for structural engineers. And it's really meant to just, let's educate structural engineers about tracking embodied carbon, tracking quantities, reporting that. And it also hosts a database of this information. And what that's meant to do, like to take it back to the LCA conversation, because there's so many different assumptions being made between LCAs, it's a useful tool for project-specific reduction. It's not necessarily a useful tool for comparing values between projects. To say unanimously, like your concrete building should be 500 kilograms of CO2 per square meter. It's difficult to use for that because there's so many assumptions being made. But what SE 2050 is trying to do is collect material data, collect impact data to do a better job of informing these benchmarks, because we basically have a really hard time establishing benchmarks as it stands. And so that's SE 2050. There's also EC3, which is the Embodied Carbon Construction Calculator. This is basically an EPD database online. You can connect it to your Revit model. You can connect it to Tally. You can upload material quantities, and it hosts industry average EPDs, but also product specific EPDs. And so it's something that can be leveraged with EPDs, to understand material selection in your region. So I can search, well, not in Texas, but if Texas had concrete EPDs, I would be able to search, like, what does 5 KSI concrete look like? What can I reasonably expect the GWP to look like? And then I can look at what's available, use that information to inform my procurement. And so it's a really valuable tool that could be leveraged. And so that brings me to, what are we doing here in Austin? So one of the main things is right here, Buy Clean Austin EPD support. So right now there are 0 concrete EPDs, and I'll talk about that. Let me Okay, so some of our past events, we've basically been holding educational events. So there was an EC3 demonstration. We talk about low carbon material reduction for different materials for concrete, steel, and timber. We've been involved with the climate equity plan. We're holding an LCA workshop at the end of the month. We've done and we're hoping to do an SE 2050 overview where we want to play a big part in outreach, coordination, and mentorship, making sure big and small firms are all involved in embodied carbon reduction. But we would just want to address embodied carbon on a local level. But one of the initiatives I'm really excited that we're doing is getting Buy Clean in Austin. What Buy Clean is it's basically a procurement policy aimed at it, and how it basically works is a government says, or local government says, okay, as the city of Austin, I'm going to require EPDs for concrete or steel or all these different materials on my project starting, let's say January 1st of 2022. I let all the suppliers know that so they can get set up to, and maybe I help them get set up to produce EPDs. And then we start producing EPDs. Once we collect data for a year and a half, then we set a GWP limit. And then we say, okay, next year you have to be below this. After a year, we say, okay, you have to be a little bit lower. After that, a little bit lower. Because you can't reduce what you're not measuring. So we're trying to get to a point where we're actually measuring this stuff. And so you can see from this graph here, California has a whole bunch of concrete EPDs. Texas isn't on that list. We have 0. Nobody's producing EPDs, and none of them are NEC3. So that's sort of a high-level view of what Buy Clean is and why we're doing it and why it's important. The point is we can't reduce what we're not measuring, so we need to start measuring it. And even without concrete EPDs or material EPDs, what you can do in your specs, because if you say, I want an EPD, they're going to say, okay, you need to pay this much money. What you can do alternatively in your specifications, you can say, I tell the concrete or tell the supplier, you can either provide me an EPD or tell me explicitly that you cannot provide me with an EPD. And so what that does is there's this kind of like catch-22 of if nobody's asking for them, so we're not producing them, and nobody's asking for them because you're not producing them. So it's, or they're not producing them because nobody's asking, and nobody's asking because they're not producing. So let's start asking, let's start bringing it up. So to recap, there's embodied carbon, there's also other impacts, and that's versus operational carbon. They're both important. We're building a lot, so we need to address new construction. Wood is complicated, we need more data, more research, and we need to put it to use. All biogenic carbon models are wrong, but some are useful. And so it's important to understand the assumptions to inform how we use them. We need more sustainably harvested forests. We need afforestation. We need to grow forests. So make sure you specify certified wood. Let's lean on existing infrastructure like FSC requirements. Step 1, use less material. That's bar none. That is the best thing you can do. Step 2, use better material. And then proportion your efforts to the outcome. Understand where the biggest impacts are and then look at those first. And then art imitates life, imitates art. Material suppliers will do what people are asking of them, and what people are asking of them will be informed by what they're producing. So let's start asking for EPDs, then hopefully they'll start producing, and then we can ask for more EPDs, and then we can use that to drive reductions over time. And talk about embodied carbon, bring it up, have these conversations as early as possible. Because we need more LCAs, we need more EPDs, we need more people talking about this stuff because it's a really big problem. I know I went a little bit over, but I hope all of you enjoyed that information. I'd be happy to, I don't know if we're going to breakouts or if we want to do questions.
Yeah, that was great. I guess just for folks that weren't part of my series, the session number 3 in the series, that kind of gave an overview of the DDX, and within the DDX, there is a question about if your LCA model used biogenic carbon or not. So that's why Martine is talking about biogenic carbon so much in this. I just posted a link to kind of where all those recordings are. So if you did not attend that, you can go onto the AA Austin website and see a recording of session number 3 and see kind of where that biogenic carbon question is on the DDX. And just kind of in framing this to the 2030 commitment, I think it's important to start to kind of record and model our embodied energy, just so we kind of know where we're at, so that we can kind of set a goal on where we're going. Similar to like the EPD data is that we need to have that data to know exactly kind of where we are, so we can start to set those goals. if anyone has a question, feel free to kind of speak up in the next 30 seconds or so. If not, I'll kind of send us to breakout rooms relatively quickly. Okay, I'm going to take that silence because there's no questions. So we're going to go into these breakout rooms with our leaders. I'm hesitant to say experts because I don't feel too much like an expert, but this is to kind of create a more of a kind of community around sustainable design and around the 2030 commitment. So while we do have our kind of leaders here, it's really kind of creating these groups to share questions and successes and really kind of build up the knowledge base of sustainable design in Austin. So I'll start to kind of put everyone in rooms. If y'all could exchange contact information and kind of names and where you're from, and if y'all have any questions for the leaders, that would be great. Just so we can kind of get these groups together and start to make an impact.